morning, everyone. This is the beginning of the fourth module where we'll take 6 hours to look at systematic problem solving and applications. We already have a flavor for systematic problem solving in the assignments in the first 3 modules. So I will go over that step by step and do some examples here. If there are any particular problems that you would like to discuss, please put it upon the forum and I will pick it up here. Before I go to solving the problem, I'm going to take time today to briefly tell about certain common equipment, devices or machines where thermodynamics is the starting point of the understanding. When we put these things together in a sequence, we make cycles. So today we will spend time looking at the common thermodynamic devices, look at the processes that happen in them, and see what are the major assumptions and the reasons why we make those assumptions in solving the problems. So we start by looking at a list of some of the common equipment which you will come across in problems. I've listed here a bunch of them. We'll begin with looking at positive displacement devices. So these are devices that either compress or pump, or the opposite thing, they take high pressure, high energy fluid and deliver work. Positive displacement is the reason for giving this name, and when we look at the construction of these, we will know that how these are different from other types of devices. The next we will look at is a heat exchanger. This is a very common device, and basically here hot fluid gives energy to a cold fluid. So the temperature of the hot fluid decreases, the temperature of the cold fluid increases. The next category of equipment we'll look at is what I listed here as compressors, fans and blowers. These are centrifugal devices which either increase the pressure of a gas or a fluid or a liquid, or they don't increase the pressure too much but deliver large flow rates. The fourth type of equipment we will look at is what is known popularly as a pump. And in particular, in this thing, we will look at centrifugal pumps. Now, just to remind you that the most commonly used engineering machine all over the world is the electric motor. And the second most common machine in use is the centrifugal pump. So that's how common these devices are. And we will look at that. Then we'll look at a turbine. So this is a device in which we put either steam or gas and expand it and get work out of it. That work can be used either for propulsion or for generating electricity. Then we'll look at what is known as a valve in general, and in particular we'll look at a type of valve which is called the expansion valve, in which we expand the fluid without much change in kinetic or potential energy. We'll look at that. This is what actually happens when in a pipe you put a restriction, it dissipates energy, there's a pressure drop, but the velocity doesn't increase too much. Nozzles and diffusers are devices that have a specific purpose, that in the case of nozzle, we want to accelerate the fluid to achieve a particular purpose, whatever that is. And the diffuser, we want to decelerate the fluid. So we'll see where these two get used. And then we will look at something which connects things in a system. So it's a refrigeration system or a power plant system or anything like that. So we pick up some equipment from these and connect them to each other, and we produce what is known as the cycle. So we look at how do we do analysis of pipes, tubes or duct. in thermodynamics. You will also come across these and many of these in your fluid mechanics courses also. So they are not very much different, but in the fundamental sense, all of these devices have to obey the laws of thermodynamics. There is no exception to this. We will also add two more things to it. One is what I call is a mixing process, where in this case, we take the same fluid at two different states, put it together, mix it to produce something else. And the last thing we'll look at is filling, or you may call evacuation, of a tank or a reservoir or any such device. So what we are doing is, in this case, putting fluid into a chamber or drawing fluid out of it and not being able to maintain the state inside. So that's why it will be filling or evacuation. So with this, we largely cover all the equipment that are there from which we can create thermodynamic systems. Or if we get a thermodynamic system, we should be able to identify which of the equipment is in which category. And today we will see what are the salient features of that. And tomorrow I'll show you some more pictures of these devices, what they look like in the real world. So let's begin it by first looking at a simple example. And the one that I've chosen here is a refrigeration system. So a refrigerator or an air conditioner, whether it is the domestic one, which is a small little device, or could be a big one, which is like a centralized air conditioning system where the equipment is big. They all have four basic equipment. One is the compressor. And as the name suggests, it takes in low pressure vapor and produces high pressure vapor. High pressure, in the process the temperature also goes up. The second device we have is the condenser, where we condense vapor to a saturated liquid or slightly a subcooled liquid. The third device is the expansion valve, where the saturated or subcooled liquid goes in, throttle, it changes phase and the temperature drops. And it is this drop in temperature and the cold fluid that we get, which we send into the evaporator. And the name suggests what we had was a mixture at low temperature of vapor and liquid. This takes heat and the liquid evaporates to become vapor. In the process, it draws heat out from the surroundings where this is and gets heated up. So we have four major equipment whose thermodynamics we know how we are going to analyze. And to complete the cycle, we say that this will be connected to this in this manner. The outlet of the condenser will be connected into the expansion valve. The outlet of the expansion valve will lead to the evaporator, and from the evaporator we send it back to the compressor. So we have four equipment, and what these are tubes or pipes. And the diameter, the length, the material, their design requirements, they could be different in the four sections. The fact is that we assume that we have also connected them with pipes from the outlet of this to the inlet of this, and like that, the four pipes. And the next thing we do is, we say, look, I want to do the analysis of this. So I have four equipment and then four pipes. So there are 8 components that complete this system. And we can say that the flow in this is like that. So we can even put a arrow like that and say that, well, the material flows like this. And to that we can, inside this we can also add what is the material that is in there. So you can put there, say, R122 or 134A, and it tells you what is the working substance that is flowing through this. And we'll now go through the individual items and see what is it, how can I do the analysis of this. And then we will say that how do I do the analysis of the tubes or the pipes. And finally, what is it that I can put together and say, look, I want to design something to do so much cooling, or I have a system and I want to make measurements and understand how well it is performed. Either of those could be our objectives. So one is a performance objective, the other is a design objective. So one of the things we do in the beginning here is that we say that in the pipes and the tubes, we assume that there is very little pressure drop or heat transfer. That means the state of the fluid coming out here is the same as the state going in there. So in this pipe, the state of the fluid is not changing. So we can say that this entire length, we can denote it by state 1. The same assumption tells that we assume that in this pipe, there is no pressure drop, no heat transfer, there is just an ideal flow, and so there is no pressure drop from the outlet of the condenser to the inlet of the expansion valve, no matter how long this pipe may be. And all of this is the same state, and this we will denote as 2. The same thing we do in this pipe. We say that from here to here there is no change in properties, and so this we will call as state 3. And the last one is from there to there, and this we will say is state 4. So we have 4 states to work with, and in either case, whether it's design of a problem or analysis of an existing system, we essentially are looking at information about these 4 states from which we can calculate the performance of these 4 devices based on what thermodynamic relations happen in the processes. This is the starting point of all things where there is a cycle. And there are many, many things where even if it is not a thermodynamic cycle in the sense that we have learned here, even if it is the flow system, we would begin by looking at an analysis like this one. In such cases, what we can also do is, we can say that I want to have one picture which gives me a complete information about everything that is happening here. And so what we can do is, we say that at this point, I'll put a line and put this thing here, and say that here I will write the pressure P, the temperature T, and here I can write the mass flow rate and the specific enthalpy. In case there is a wet state, we make a small change. Because pressure and temperature are the same, we can give either pressure or temperature, and that we'll have to mention the dryness fraction there. So what we have basically done by putting this type of an information here, and these could actually be the numbers, the real numbers that are there. We specify what the units are, and we can say that, okay, this is in kilopascal, the mass flow rate is in kg per second, the temperature is degrees Celsius, and specific enthalpy is in kilojoules per kg. So each state gets completely defined on this diagram. And if you look up such diagrams from any manufacturer, say of a power plant, they will write one more very important piece of information which says that, okay, for this substance, I am telling you that these are the properties, but how did I get these? And so they will always write what is the source of the properties. And as I have put out the solutions for the 3rd module, what happens is there are many places from which one can get properties of any working substance, including many online websites. And if you use one or the other, you will see slight differences from one source to the other source. In some cases, the differences will be very small. In some cases, the differences could be large, in large part because the reference state at which they have taken S equal to 0 or H equal to 0, that is at different temperatures. So the absolute values could change in that case, but what happens is that as long as we are consistent in using the same property source, we don't have a problem. Because in almost all these cases, wherever we are looking at changes in properties across a device, we invariably come across difference of two properties, H1 minus H2 or S1 minus S2, and that difference is largely independent of the source from where these properties are taken. So if the designer of the system used a particular source and we are checking that calculation based on properties from some other source, this could be a book or a table or a website, we could find some differences in the values that we get over here, but largely the differences will be small, but in the end there will be some deviation from what has been given because of the source, and the second deviation will also come because of round off. The property tables that you would have come across, in some cases they are up to 4 places of decimal, some 5 places of decimal, in some cases only 2 places of decimal. And that is given because it means that those are the significant places over which the designer of this property is confident that there is no error in that. The next place of decimal is in doubt. So if you are doing calculations and giving answers, we must not add too many more decimal places after that, because your source did not have that much accuracy to begin with. So please keep that in mind when you report answers to a calculation. The calculator may give you 8, 9 decimal places, but in the end, the goodness of your property is how good your final result will be. You cannot do anything more than that. Please keep that in mind. So the round off is an important feature. So there will be cases where we have done round off in the solutions also, somewhere 1 decimal place, somewhere 2 decimal place, and you could find that there could be a small difference between what you get and what is there in the solution. In case there are doubts, please do post it on the forum. I will cross-check and clear those doubts. But the important part is the source of the properties in the round off will cause differences in numerical answers. But the formulation of the equations, if that is correct, most of the things we have done right, the next step can easily be checked out. Okay, so this is how we will put together things for a cycle. But there are many cases where we will not be studying a cycle. In the application, we are only going to look at one component. So in that case, we will just take one portion of this, only this part, and give the inlet outlet states here and there, and do all the analysis from that point. So the same process we will follow for a single process. A device like this is a flow system, and a picture like this is called a schematic diagram or flow diagram, which I hope you have learned in one of your engineering drawing courses. Almost every system design begins with this. It could be something like the fuel system of a car, but the first picture that the designer will make is, well, what are the equipment that I'm going to put, how I'm going to connect them, and decide what are the equipment that are there, and then we go about doing the engineering of the device. The same thing in a POS plant or a cogeneration plant or a combined cycle power plant. Same thing is the beginning. This is the beginning thing to design that process. Once we have done the thermodynamics of this, we get a lot of information which tells you what should be the mechanical design out of all of this. For instance, this tube, if we know what are the properties here, what is the flow rate, then we can decide that what should be the diameter, what should be the thickness, so that it can withstand that pressure, and what should be the design pressure based on the thermodynamic pressure that has been told to us from this side. The evaporator, for instance, we will know that we need to go from this state to this state, and so much mass flow rate is there. Then we can calculate and see how many tubes are required, how many fins are to be put, what is the physical shape and size of it, what should be the pressure for which the tube should be designed so they don't rupture. All those designs follow this fundamental information. So in the design of all of this, this particular type of a system is hugely important, and it's important we get it right. Okay, so this is the idea of a schematic or a flow diagram.